Good afternoon, everyone. I was having a little problem with my audio and I had to reboot, but I'm good now. I think you can hear me okay, right? Just hit the thumbs up button. All right, excellent. Thank you. Okay, so we are going to continue the review that we were doing real quick, and then we will start on new stuff, hopefully next time. Okay. I am sharing my screen so you can see what we're doing. Right, so we're going to go to modules. And I've been posting the lectures up here. I don't know if you can see them. I'm going to show you where they are. You see it? That was the last lecture we had. So I posted it up there. I'm recording this so that you can see it. Right. So we did not finish looking at this, but we started looking at ionic and covalent. We looked at ionic, how to name things, and we're going to go there next. Now, remember, this is a review, so you've already seen this prior to now. And I need for you guys to, let's see, Christopher, what? I'm trying to see who's here too. Okay. So with this one, we stopped at covalent compounds, I believe. It does have a file associated, it just does that. It's crazy. Okay. So we looked at the naming. We looked at all of this, how to make compounds, because this is very important. Sometimes I may just refer to your compound in the name, by the name, not by the formula. And you need to know what that is. Okay, this is a very useful table. I think this is where we stopped, where you can look at and you can see all of the elements that would have a Latin name and those that do and don't use the Latin name, and those that don't have a Latin name, yet they are still named with this. Now, the only thing with this Latin naming is that when you have more than one option, like sometimes like vanadium can have quite a few valences. If you have more than two, I mean, then you don't have the ic in the OUS anymore. You have to go back to the IUPAC naming. And that's what one of the disadvantages of this is, and that is why it's no longer used. Like I was telling you, chemical companies still use the ferric and ferrous and cobaltose and cobaltic and things like that, but we don't use it officially anymore. Anyway, so in this case, when you do both of these, you are going to name copper chloride, right? Copper 1 and copper 2. Okay, so you notice that this is copper 2 chloride. This is zinc chloride. This is cobalt 2 chloride. And this is mercury 1 sulfide. Now, and mercury 2 sulfide. So it's saying to do both, and there we go. See, in order for you to know which ion you have, which positive ion, because all of the negative ions, all of the anions are always ending in "ide." But the ones that are positive, and that have multiple valences, you have to differentiate them by using their valence in parentheses, Roman numerals, okay? Why not regular numerals? Because we're already using regular numerals and it would get very confusing when we do. So they had to use a totally different one than the one that's already used. And you notice that in chemistry. Everything has a place and everything has a purpose. Okay, so now the polyatomic ions, and I told you I would give you a sheet of this, which I will, as a matter of fact. That was calcium hydroxide, copper 2 sulfate, ammonium nitrate, and cobalt 3 carbonate. We did these, I remember. Now, covalent. This was where we stopped, right? We were doing the exceptions. Sometimes when you have a combination of 2 letters, like AO and OO, you drop the first letter. But with I, you have to keep it. You cannot say doxide, you have to say dioxide. Okay, so naming these, let's do it. Okay, you can either do it via chat or you can do it via voice. Doesn't matter to me which one, as long as you participate. Okay, nobody's answering. Okay, so we have 4 of them, right? And that prefix for 4 is tetra. So this would be carbon tetrachloride for the first. Oops, I didn't mean to show you the second one yet. All right, the second one, we have 2 phosphorus and 3 oxygens. So the prefix for 2 is di. The name is diphosphorus trioxide. Remember, everything ends in IDE, unless you're a polyatomic ion. And this one is 1 iodine. And remember, we do not use mono for the first element. We use it for the second one, but not for the first one. So mono, and 7 is hepta. So iodine hepta, not septa, hepta, heptafluoride with an H. All right, so there you go. Very good. Thank you. All right, so that would be the conclusion of this PowerPoint. And like I was telling you, this is, now if you want to redo some of these, revisit some of these other sheets, you can. And as a matter of fact, I'm going to go back to this module and show you where your practice is. Now, the other part that remains for you to remember is how to name acids. Yeah, right here. Okay, so here's your, see, there's the polyatomic ions list that I told you I'd put up there. And there's your naming practice. But I told you I would give you the whole packet, which I didn't, which I need to do that. I need to give you a whole packet of ionic and covalent compound. Wait, this is it, isn't it? No, that's the chat. Okay, so no, it's not here. All right, so if you want to do any practice, you notice there's naming practice right here. Right, next is our acids. And for that, I'm going to have to share my something else. I'm going to use the screen, the whiteboard, just as if I'm writing on the board here. Okay, for acids, and I'm going to use text. So when you have an acid, Remember, it always begins with hydrogen, always, okay? That's the first thing you gotta remember. And then you can have two kinds. You have this one kind and you have this other kind. The first kind is known as a this one is known as a binary acid because they have two elements, okay? Okay. And for that, the rule says that you need to use the root of the anion, that's the negative, right? End it in ide. No, ik, sorry, ik. And then of course the word acid. But before that, use a prefix known as hydro. So for example, then, okay, before use the prefix. So before everything, right? That's called a prefix. So before, boom, want to do it like that. So you know the prefix hydro and the root of the anion ending in ic acid. Okay, so an example of that would be this. Example, HCl. Okay, so how would we name it? Well, we name it hydro, and we use the root of the chlor, right? So chlor, oops, chlor, and then ic acid. See that? Okay. For the other side is no, oops, sorry about that. The other side is known as a ternary acid or oxyacid. Oops, let me get my text box. Here we go. Okay, so this is known as a ternary acid, or also known as an oxyacid. Oxy because it contains oxygen. Okay, and ternary because it contains more than two elements. Okay. Now, how do we name it? Well, the rules say that if your polyatomic ion ends in 8, you change the ending to ic. If the polyatomic ion ends in ite, then you change the ending to OUS. Oops, not PUS, OUS, sorry. All right, example. Here's an example, several examples. Okay, so we have HCl, CLO, oops, O, okay? This one would be known as, since the name of CLO is hypochlorite, right? So you would take the ite, right? We would take that off and would change it to OUS. So we need now to just erase that, hypochlorous. And of course the word acid. I'm not gonna write the word acid after each example. Then you have HCl, ClO, Lord, O2. And I am not able to do subscripts on this particular writing, so just imagine it is below. And this name of this one is chlorite acid, right? Because, oh, so it's chlorite. So in changing the I to OUS, and then the name is chlorous acid. Then we have HCl-O3. Oh, Lord, my fingers just don't stay on there. This one is known as chlorate, right? So you take the 8 and you add ic, and then it's acid. You see that? And then the last one is HClO4. And this one is known as perchlorate. So take the 8 off and put ic. See there? Oh, and then I am putting acid after all of them, and it doesn't take that long. All right, so there you go. These are your examples. So any acid that you have to look at two things. How many elements? And does it contain oxygen? Actually, it's my way of doing it. But binary acid just means 2 elements. So HCl is 1. If you had HI, how would you name it? So here's my question to you. Name HI. And then here, I want you to name, and sorry about the superscripts, but I mean subscripts. Okay. So somebody wants to volunteer. You notice I gave you which place it belongs, so just follow the rules. You can either do it via chat or you can talk about it. Either one, I don't care. Okay, almost. Okay, so it's iodide, right? Right? So iodide, change the iodic, and you got it. See? Very good. Okay, so in this case, I'm going to put it below here since somebody already answered. So the name of the anion is iodine, iodine, right? You take that ending, "ine," and take "ic," and then acid, and that's that one. What about the other one? I'm waiting for an actual answer here. You have a polyatomic ion list you could be looking at that I posted up there for you. If you download that, you'll find it. When I made that polyatomic ion list, I made it in order of alphabetical order, but by element, not by name. Usually follows suit, not always. So I had to pick one. It actually works better by element because things like ClO, ClO2, ClO3, ClO4 stay together, whereas hypochlorous, chloric, and perchloric would not. The H2 is throwing you off, okay, but it starts as H, right? So that part's not what needs to be looking at. You need to look at your SO3. What is the name of SO3? The H2 is just means that it's an acid. The acid's there. And I'm going to show you how it all works. Not sulfuric, because it's sulfate is for sulfuric. What is this one? It's not sulfate. It's See, if I actually write down, yes, it is sulfite. So what does it say? If it's ite, change it to? Yes, very good. That is the name. Sulfurous acid, okay? Because this is sulfite, right? So if we took sulfur, right? This is one of those examples where there is no, you cannot use sulfurous acid, okay? Because sulfide, right? I always say take off the "ide," but in this case, you got to go back to So it's OUS, sulfurous acid. Yes. Okay, very good. All right, excellent. All right, so let me show you why that needs to be the way it is. Okay, so you have hydrogen, right? That is like this, and you have this polyatomic ion that is known as sulfite, which is an SO3 2 negative. This 2 needs to balance with this one because this compound needs to be neutral. So in order for this to be balancing, right, you need to take the 2 multiplying, and that gives you 2 positives. And then 2 positives and 2 negatives cancel. You see that? That's why we do the crisscross. It's so that the balance is out. Does that make sense? That's why the H2 is there. Now, let's say we had this one. And notice I'm not doing anything yet. Okay, so we have hydrogen, and PO4 is phosphate, right? And phosphate has a 3 negative charge. So in order for us to make this balance, what would we have to do? Okay. Yes, so if you cancel, how would we cancel out the 3 negative charge? Yes, but the hydrogen only has a positive 1 charge. So what do we do to the hydrogen? Okay, so what does this mean? When you see a subscript on an element, what does it mean? Okay, nobody remembers that one? What it means, a subscript down here, means you have 3 of these. And if you have 3 of these, you have a 3 plus charge, don't you? That's right. How atoms of the element there is. Yes, how many atoms, exactly. So when you multiply something times 3, right? You end up with 3, well, something that's positive, 1 positive times 3. You have 3 of them, you end up with a positive 3 charge in the molecule. And that's exactly what you want, you see? So that's why you do that. You cancel the charges by putting this number here. That way, when this is a 1, right, it balances. Okay, so that's that. All right, so we're going to stop sharing on this one and go back to sharing on the other one. And it looked like I'm sharing the same thing. Okay. So that's how you do ionic and covalent. The next thing that we're supposed to remember is how to do Lewis structures. Now, Lewis structures is an easy thing to do, but you have to follow the steps to the letter. And I'm going to show you the steps in this PowerPoint. It's really good. Don't worry about Page numbers or anything, I keep forgetting to turn them off. I mean, you know, I used the PowerPoint for another book, but it doesn't matter. It's still what we want. It is the right PowerPoint. It's just I keep forgetting that we don't need all of this. Okay, so we are looking at this guy. All right, so here is our molecular structures. In order for us to be able to know what a molecular structure something is, we have to have a Lewis structure or Lewis diagram. So this is what you have to remember. You have an octet rule. Octet meaning 8, which means that atoms form bonds to have 8 valence electrons. If you don't recall what valence electrons are, they're the outermost shell electrons. Okay? But there are exceptions. And there, hydrogen, for example, it doesn't need but 2. If you look at here, let me get my little pen so I can annotate here. If you look here, hydrogen itself only has 2, right? You see that? In both cases. It doesn't need more. Whereas oxygen, if you go around oxygen, let's use a different color for oxygen. Let me do that. Let's do red for oxygen. Okay, see this? Oxygen has a full octet. Okay, and that's what we're looking for. All right, so let's look at this. Okay, let me go back. Erase everything here. All right. All right, and another example is boron. Oh, sorry, I went too fast. Groups 1, 2, 3. Okay, groups 1, 2, and 3 on your periodic table. They're 1A, 2A, 3A, or 1, 2, and 3, either one. They get 2, 4, or 6. So that would be the groups with lithium, with calcium, and with who else is in here? Boron and aluminum. Yeah, those are the ones for, okay, they get 2, 4, and 6 only. So like right here, let's look if we're following. See, we don't necessarily have 8 around this guy. But you notice fluorine, on the other hand, has 8. All of them do. You see that? 8 dots. And the dots are put exactly like this. You can imagine that you have a box. Let me do this with a straighter arrow around the thing, and that your box needs to touch these little lines. See? And you can only put 2 in each side of this box. So that's kind of how this works. See, if you have a box, see how they're sitting right on top? Okay. And touching, that's how you put your dots around an element. All right, so let's clear that. And let's keep going. So those are your exceptions. Groups 1, 2, and 3, remember that. And sometimes you have expanded octets, which this is the time where we're looking at it because we are in Chem 2. Expanded octet means that you can have more than 8 valence electrons. Because of covalent bonding, this is a thing. It doesn't normally happen, but covalent bonds are different and they can share more electrons than there are. Like, let's look at this guy. And by the way, this is another way of writing Lewis structures, which I prefer because now you know that these are the bonds. Each one of these lines in here represents 2 of those electrons. So if we were to circle Mr. Sulfur, oops, let me go back. Sorry, I meant to get this guy. Okay, if we were to circle these, you can see that you have 2, 4, 6, 8, 10, and 12 electrons around it. So it's defying the octet rule. It's actually called an expanded octet because it has 6 pairs around it rather than only 4. Sulfur is one of the elements that can expand its octet. Right. Look at fluorine though. If we circle fluorine, you can see it only has 8, which is what you expect, 2, 4, 6, and then this one represents 2 more. So that's 8. All right, let's clear that. And let's keep going. That's, like I said, that's an expanded octet. And then you can have radicals when you have odd number of electrons and they're incredibly unstable because nobody wants to have a lone electron around them. They're going to be looking for a pair. That's one of the things that you'll notice. They come in twos. Okay, so here's your rules. You might want to take a screenshot of these once I tell you which one's the last rule. Rule number 1, you find the total number of valence electrons. Rule number 2, or sorry, not rule, step number 2, arrange the atoms where the singular atoms are in the middle. In other words, the ones that you only have one of is usually in the middle. Another way of seeing it is whoever's least electronegative is going to usually take the center spot. Okay, form bonds between atoms. That's the lines. Distribute the remaining electrons to give each of the atoms an octet, recalling those exceptions, groups 1, 2, and 3. Remember that. And the last one, if there aren't enough to go around, form or double or triple bonds. Okay, now you can take a screenshot if you want, because this is exactly what we have. These are your steps, and we're about to apply them. Okay, ready? All right, so here we go. Number 1. We're going to do a Lewis structure right now. CF4. How do we get the valence? Okay, so we're looking at carbon. Carbon is in group 4, which I don't know if you recall this, but a group number tells you how many electrons are on the outer shell. So the valence electrons. So carbon brings in 4 electrons to the pot, right? Fluorine brings in 7 because it's in group 7, but there are 4 fluorines. That gives us 28. So adding these up gives us a total of 32. That's step 1. Step 2 is to arrange them so that the central atom is in the middle. We said it would be the singular atom, or the one there's only one of, that would be carbon. And it's also the least electronegative of the two, because fluorine, remember, is the most electronegative element in the periodic table. So next step, 3, we need to make bonds. One of the things it doesn't tell you on the steps, and this is something you need to know, is after you make the bonds, you need to subtract that number from the total. So you just use 2, 4, 6, 8 electrons, right? Because you got 4 little bonds. Subtract those, you have left 24. For fluorine, since it already has 2 electrons, see, carbon is just fine. It has 8 electrons around it. 4 little lines, right? Each line represents 2 electrons, so it's got 8. But fluorine only has 2. So it needs a total of 8. We need 6 more around it, right? And 6 times 4 is 24. And there you go. You have 0 electrons left. That's how you do Lewis structures. Next one. This is one of the exceptions. Beryllium is in group 2, right? So it only has 2 electrons. Chlorine is in group 7. There are 2 of them. You got 14 there. Add them up. Do your screwed sketch. Make your bonds. Subtract. You get 12. You're probably thinking, 12 is not enough for beryllium. You're right, but beryllium's an exception. It only needs 4. It has 4. So beryllium's fine. The only ones that aren't fine are chlorines. The chlorines need 6 apiece. 6 times 2 is 12. Perfection. No more electrons. We have finished them. So this worked really well. Next one is carbon dioxide. 1 carbon, 4 electrons, 2 oxygens, 6 electrons, total of 16. Do your thing in the middle. Do your bonds. Subtract the bonds, you get 12. Now here's a problem. You can look at it and say that that's not going to be enough. Then you would be correct, because you have 12 electrons, but you actually would need more, because carbon, after you distribute the 6 electrons each on oxygen, carbon's going, wait a minute, you shortchanged me. And you did. So what you need to do, and this is what I'm going to show you, you take this guy and move it here. So then you need to erase that guy, and this guy, and move it here, and you need to erase that guy. Now you see how carbon now has 2, 4, 6, 8 electrons around it, and oxygen still has 8 also. So let's keep going and do this. Let the computer do it for us. Oh, okay, sorry. There it goes. It did it for us. You see how it disappeared? All right, so that is the total. Another trick that I'm not a trick, but it's more like a kind of like a proof, kind of like a Matthew proof things. You start with 16 electrons. If there are 16 electrons present in your structure, then your structure is good. Let's see, 2, 4, 6, 8, 10, 12, 14, 16. So it is good. What if you had put 3 on one side and 1 on the other? Then your structure would still be okay, I guess. Let's see, if we put 3 here and 1 there, we would have this one gone. So we would have 2, 4, 6, 8, 10, 12, 14, 16. So how do we know this is the correct one? Because we needed 4 electrons, and usually when you need 4 electrons, it means double bonds. Okay, and clear that. All right, so now polyatomic ions have an added step. The step for polyatomic ions that you're going to add is your charge. You add 1 electron for each negative charge, and you subtract 1 electron for each positive charge. So, and then to indicate that this is an ion, in fact, you need to put brackets around the ion and put the charge outside of it, like this. ClO4. Okay, 1 chlorine, 7. 4 oxygens times 6. That gives us a total of 31. Remember we said we don't like odd numbers? Well, guess what? This extra electron is contained in this structure. So we need to add 1 more because we have a negative charge, right? So that gives us 32. Now we do our thing, make our bonds, subtract the number of electrons we use for the bonds, we get 24. Chlorine is happy, it has 8. Oxygen needs 6 apiece, and 6 times 4 is 24. Now, last step. Everything's good except one thing. We need to do this, the brackets, and label the charge. Because otherwise, this structure would be totally different and it would be wrong because you wouldn't have that extra electron. If you don't have the extra electron, you cannot make this structure. All right, NH4. Same thing, 1 nitrogen, 5 electrons, because it's in group 5, remember? And 4 hydrogens, group 1, 4 electrons, total of 9. It has a positive charge, and we said we need to subtract 1 per positive. So we only have 1, so it's 8. Let's make our little diagram. Put electrons towards to make a bond. That's 8 of them. And you notice we have 0 electrons, and that would be correct because hydrogen does not need but 2 electrons, and it already has them. And nitrogen has its 8. So this is a good structure. Now, let's do the bracket and label the charge, and we're done. Now, there's something called resonance that some atoms, some molecules, experience. And that is because you have one double bond that can be placed many places, like this. And to be accurate, the Lewis structure should be the average of all possibilities. So what you do is you separate every structure that is possible by a double-headed arrow, which means it can go either way, right? Double-headed means usually an arrow points the direction towards the head of the arrow, right? But if you have a double head, it just means it can go either way. Like right here. This is ozone. See how it can go? The double bond can be on the left or it can be on the right. And this is SO3. Let's do the math. Okay. We're going to do it. I know you can see all of this, but that's okay. We're going to do the math anyway. We got 1 sulfur, right? Let me make it. Yeah, that's good. It's group 6, so we have 6 electrons. We have oxygens. We have 3 times 6, so it's 18, a total of 24, correct? No, this is not SO3 negative. This is not sulfide. This is sulfur trioxide. If we had a negative, this is why it meant, this is what I was telling you. It would be -2 anyway, but it's not. This is sulfide. No, it's not sulfide. It's sulfur trioxide. It's a compound, and it actually has no charge. Okay, so once we do our little Lewis structure that we know goes like this, right? We subtract 6 from that, we get how many? 18 again, right? 18. 18 just goes around this guy, and this guy. Notice sulfur is going, where's mine? So that's why you need to introduce that extra bond. So you need to move one of the Lewis structures, which I'm gonna, let me see, let me undo these. The circles, I need to take them off so we can do these dots. Okay, so we're going to introduce, that's what it would look like if we actually did it. Oops, sorry, sometimes my dots don't fall in the right spot. I'm doing this with my fingers so you can imagine how hard this is. There, I'm going to redo those because they look terrible. Okay, there and there, at least that's better. Okay, so let's say, okay, I know that I need 8 electrons around sulfur. So I'm going to take these 2 and I'm going to move them to the middle, which is perfectly fine, right? See, that's one of these structures. That's this one right here, right? Oops, I just erased all my stuff. I did not mean to do that. Sorry. Okay, just one stuff, nothing else. All right, so we are now moving, or we could also leave this one alone, put these back and say, oh, we're going to use these right here. So we're going to make the double bond here, right? And we can, and that's perfectly fine too. See how it's a possibility also? And there's one more possibility, isn't there? So now we return those to this one. Let me first erase this thing and turn those to this one right here. Boom, boom. And say, what about you? You can be the one and you can be right. Once again, we can move it over here. And all those are possible Lewis structures for this guy, okay? See, every one of those is possible. Therefore, when we write it, we need to write all of the possibilities. And those are right here. I'm going to show you here in a minute. There you go. Let me just clear all my drawings, but there you are. There's all the possibilities. And that's why we need to do that, okay? And see, I would know, if I looked at this structure, I would know that this SO3 is the right SO3 because it doesn't have brackets and it doesn't have a -2. So this is sulfur trioxide. What would happen if we did SO3 -2? Well, let's do the math. Let me take you to another place and show you that, and then we'll be done. So we're going to do the board again. This time I'm going to have to use my finger because I can't write. Right, so the next one that we're doing is SO3 -2. Right, like this. All right, I should have put it over here because otherwise I'm going to get in my own way. All right, so we have 1 sulfur times 6, 3 oxygens times 6, plus 2 more, right? That gives me 26. You notice so far that's already a difference. Before we had only 24. So now we have SOOO. Okay. Notice we have 26. So we're going to start, you always start with the outside. So we're going to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Remember, we use 6 for the bonds too, so I forgot to do that, but there you go. We had 20 left. See how now we have enough? So this is not SO3, it's SO3 -2, which is why we need that. That was just a point I wanted to make. See how we don't have resonance and we don't have less electrons. We actually have enough. All right, that's that. We are pretty much done with this part. Let me clear that. No, let's not clear anything. Let me just go back to new sharing. The same thing again. Okay. All right, so let's escape that. Now, when you have Lewis structures, there are things that come around, and I'm going to show you what those are. I need my mouse back. There we go. All right, so let's turn this one off. Okay. When, like I said, when we have that, I'll go back to modules. The thing that comes with it is known as geometry. And I'm going to give you the most important thing in this geometry thing, which comes from the Vesper lab right here. The most important of all the things that you're going to see right here is this one table. Hold on, it's loading. Well, actually, let me just click on it. Probably loads faster this way. Yeah, it does. There we go. There it comes. Takes a little time. All right, here we go. Yes, let's open it. All right, so we are looking at this table, very important, not that one, this table. This is the table that you want to know, because this will give you every single possibility of a non-expanded octet geometry, which is what we're reviewing. We're reviewing the non-expanded octet ones. All right, so you have number of electron groups 2, number of bonded atoms. You notice that no electron groups doesn't always match the bonded atoms, because we have what is known as a lone pair possibility too. We just did SO3, okay? Oops, let me get this guy better. There we go. This SO3, which is sulfite, okay? Sorry, I keep hitting this chat thing. Okay, -2. There we go. All right, so let's look and see if we can categorize it. How many electron groups do we write? And you notice we're just looking at the central atom. So I'm going to circle in red that what you need to focus on, okay? Just the central atom, just this part right here. Nobody else. Because the other things are what makes the central atom have its shape, but this is what we need to know the molecular structure. Okay, so you see one group, right here. So we'll check it. 1, 2, 3, and 4. So we have 4 groups, yes? 3 are bonded, right? 3 are lines. See, 1, let's do a plus on these. Okay, the ones that are bonded, plus, yes, plus here, right? And then here. And the one that's not a plus is this one, so we're gonna put a minus. Okay, you notice this one is not one of the bonded atoms. However, we do have 4 electron groups. That's correct. Those are your checks, right? The bonded atoms I put in pluses, right? Right. So your electron group geometry, notice it says electron group geometry, is tetrahedral. But your molecular geometry is not, it's trigonal pyramidal. And the AB3E, all it's telling you, well, this format is saying you have a central atom, that's the A, with 3 bonded to it and 1 electron pair. You see that? Which is exactly what we have, right? Okay. So let's do the SO3 that wasn't this one, the one without. Remember how it was like this? And we can just pick one of the structures. I'm just going to pick this one. It doesn't matter which one we pick. Okay. But I want you to tell me what the molecular structure of this one is. How many electron groups? Oh, and by the way, double bonds are considered one group. So how many electron groups do you see around this atom? Come on. Doesn't take long to type a number. Correct. 3. 1, 2, 3, right? Nothing else. So where would we put him? We know it has 3 electron groups. How many of those groups are bonds? Correct. So that means it matches this guy right here, right? Which means that you have a trigonal planar and molecular geometry also trigonal planar, which means it's an AB3. And AB3 just means central atom bonded to 3 things. Do you see that? Okay. So last part on this journey that we're taking today is to look at resonance. And yes, we do have resonance on this one, not on this one, right? Because resonance, there's no double bonds, you can't have resonance. The last thing is to see polarity. Polarity. We have polar and non-polar. Which one do you think is polar and which one is non-polar? The right or the left? The sulfur trioxide on the left or the sulfite ion on the right? Okay, and Alicia, you are correct. You can pat yourself in the back. You are very much correct. Do you know why? This right here makes it polar. Anything that has lone pairs around its central atom is a polar molecule, okay? Doesn't matter how many. If it has any electron pairs, it's going to be polar. Which brings us to the last thing that we're doing today, and it's very quick and very simple, is known as, and we're just going to go back to these two same ones. Okay. So we said this is non-polar, and I know I'm writing all over this thing, but you can see it. And this is polar. Okay. So there are 4 intermolecular forces that we are interested in. And I'm going to go back to the board again. And this is the last thing we're doing. So let's go one more. So we have this guy. I'm going to have to do it real quick and just so you remember who's who. And then we have this guy. And I'm going to put the dots now. Sorry, I cannot put those in there because my stuff is in my way. Okay, but anyway, so these are the 2 that we have. We said this was the non-polar. Oops, undo that. Let me go back. Okay, this is non-polar. And this is polar. Okay, so when we have a polar molecule or a non-polar molecule, the one force that can be for both is known as London dispersion forces. And I'm just going to call it London dispersion. Okay. I'm going to call it LD here. Okay. So both of those have London dispersion because they're molecules and they have atoms. And their atoms have electrons. And the electrons are what makes that happen. Okay. That's all there is. When you're polar, you can also have a dipole. DP, I'm going to call it that. Why dipole? Because since we are polar, we have an imbalance of charges within this molecule. As a matter of fact, sulfur and oxygen And remember, I'm just gonna put the O's. I'm not gonna even bother putting the other stuff, all the dots, just the one thing that I'm doing here. Oh Lord, come on. Okay, so just the O's, 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 right? Okay, so we have the forces, and I'm gonna make those in red. They're gonna go this way because oxygen is more electronegative than sulfur. This way and this way. So this is gonna charge negative, 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 right? And this is more electronegative than sulfur. So, I mean, the force is gonna actually go up like this towards sulfur because it is a lone pair. So look at here, these two will add into a force, whereas these two will cancel, right? So we end up with a net force. Whereas over here, you have S, O, O, and usually they're like this, right? So your forces are gonna go pulling this way, and pulling this way. If you know anything about vectors, you would know that these would cancel out because these two will add up and cancel the other one, okay? So, because a scalar force, remember this is what this is a vector, not a scalar, it's a vector force because it has magnitude and direction. So that's what's gonna go on. Now let me go ahead and erase this. All right, so that's your polarity. Oops, let me just undo these. I'm just gonna have to undo it a little different because I can't erase. I wrote all over everything, so it's just undo, 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 undo. Takes time. Oops. Just want it to all disappear. Yeah. All right. Now, the other thing that can happen is you can have an ion dipole force. And one of these is an ion, right? But in order to have an ion dipole force, you have to have a charged molecule. And you also have to have polarity. And the last thing that could happen, but didn't happen here, is hydrogen bonding. Hydrogen bonding happens to be a bond between hydrogen, right? I say beat because between hydrogen and what I call the phone, F, O, or N. Okay, so hydrogen has to be bonded to either fluorine, oxygen, or nitrogen in order to have a hydrogen bond. Here we don't even have hydrogen, therefore we cannot have a hydrogen bond. Water, however, has a hydrogen bond, and I'm going to show you the real structure of water. It's actually two hydrogens and two lone pairs. Okay, so the lone pairs are going to, this is going to pull up, right? And these are also going to come in and pull out. All right, so you notice they're all adding up, and this is very polar molecule, but this also has hydrogen bonding. In order to have hydrogen bonding, your molecule has to be polar, okay? And that's it. So just remember, these are your forces. London dispersion, which happens in every single molecule. Dipole-dipole only happens in polar molecules, and all polar molecules have a dipole. Ion dipole, which happens between a charged molecule and a polar molecule. for example, something like sodium chloride dissolving in water would be an ion dipole, because the ionic compound would dissolve by, dissociating the two ions, the sodium and the chlorine, in the water molecule, would end up with a positive end, right, which would be these, and a negative end, which would be this, right? The negative end would be the oxygen, which actually is how it is, okay? So when you look at that, you can see that the chlorine, which is negative, would go towards this end, and the hydrogen, which in this case would be the positive, would be, the sodium, sorry, would be going towards the oxygen, okay? Because that's the negative part. And that's how water dissociates. So this is a dipole moment with an ion dipole moment. Dipole is just two dipoles that are within the molecule. And then hydrogen bonding, which is what I was telling you, happens only between these three right here and hydrogen. All right, that's it for today. We are done. And if you have any questions, I am here to answer them. No? Okay. All right. You all have a great rest of your day, and I will see you, or not see you necessarily, but talk to you Thursday. Bye, guys.